Hi guys, in our previous video we had looked at a way of describing energy of an electron in a hydrogen-like species, and therefore we had given an interpretation of this as the summation over the potential energy and the kinetic energy of that particular species, whereby we had indicated that the value of n is equivalent to 1. So therefore from this particular case we came up with a general formula for describing this specific energy, and then we said that this energy can be represented as a negative value of m e k, whereby this specific, of course, this is so sorry for that, just to reduce this specific space so that we can be able to have a large. So we had said from our earlier discussion that we can be able to represent the energy of a hydrogen-like species by giving it as a summation of the energy of this particular species of potential energy and kinetic energy, which is going to be given as such. So for hydrogen-like species, we said the value of n is equivalent to 1, and therefore we are given a general formula for describing this particular energy as a negative value of this particular illustrations. So this is a mass of the electron, charge of the electron. I'm going to extend that one, and then we're going to have z, which is going to be a square, and then we said that one is of course a mass number, and then we can be able to give that one as a ratio between that one and nh squared, and then this is going to be 8 epsilon naught. So I'm going to elaborate on this so that we can be in a position of not having a confusion. So this is the mass of an electron that is going to be given as m, and this is going to be the charge of an electron which has been raised to power 4. This is the number of protons in this particular case, and this is going to represent the quantum number which is given as m Planck's constant, and this is the permittivity that we have given as such. So this is the general formula we had given for describing the energy of this hydrogen-like model in our first discussion. So therefore from this we can be able to expand it further in order for us to try and describe how this electronic spectra of hydrogen-like atoms can be described. Now from the relationship that we had developed from our second discussion, we had said that we can be able to describe frequency of these spectral lines of a hydrogen-like species. Now that we had earlier given the aspect of energy, and therefore these spectral lines, as we said, they were produced from the electrons changing from a higher energy state to a lower one, and therefore this change energy was described as delta E. So therefore we had an equation that is going to describe this change in energy as delta E as the difference between this particular case for E1 and E2. Therefore this change in energy, we said, is going to represent a value that is going to change from E2 to E1. We can be able to do a substitution for this one for the quantum numbers N1 and N2, which is the two specific energy levels. Therefore we can be able to illustrate this one using these two specific cases. So for E1 we shall have this one represented as the energy, which is ZE, and this is going to be M, and then this is going to be given as, so it's basically the implication of this specific where we are going to have M4 and then Z all over N, and this is going to be a square 8 epsilon naught. So for the first energy, therefore we're going to have that one illustrated as that, but we can be able to expand that specific formula so that we are able to have this value for n given as the reciprocal of a square of that particular n for the first energy given as such. So for the second one, we're going to have it given still as this is a negative z squared e 4m all over h squared 8 epsilon, and then having a reciprocal of the square of that second level given as such. So the difference between the two is going to give us a description of this delta E, which is a change in energy. So therefore, the amount of energy that is going to be experienced by an electron that is jumping from a higher energy level to a lower one is going to be given as the difference between the two. And if we try to do that one, we're going to have it being represented as the delta E being given as Z squared E 4m, and this is going to be all over 8 epsilon, and then this is going to be the square. We just confirm this one from our previous example that we had given. So basically this is going to be a square of this epsilon, but from this we can be able to see that the difference between this is going to give have a change over the n1 and n2 being given as, you can see this is a negative value, so this is going to bring the aspect of the n, this particular second value for E2 being positive. Therefore we shall have this one given as 1 over n1 square minus 1 over n2 squared, given as such. So this is going to describe the change in energy whenever an electron is jumping from a higher energy state to a lower one, being given using that change in delta. So if that is the case, then therefore we're going to look at the case of an electromagnetic radiation. Now if you consider this change in energy as a radiation of electromagnetic radiation, then therefore we're going to consider this one as a photon, which is a packet of light. And then therefore we're going to use the de Broglie's relationship in trying to describe this aspect of the energy. Now earlier on we had said that we can be able to represent this relationship by the use of this relationship. We had said lambda frequency is equals the speed of light, and therefore this one can give us the frequency which is equivalent to c over lambda, and therefore we can be able to describe the change in energy that is being experienced at this specific point as delta E is equivalent to h change in hc over change in lambda. And if we try to equate this specific formula with the change in delta that I've given at that specific point, so because of space I'm not going to wrap this one, I'm just going to change this notation for change in delta and give it as hc over lambda. So therefore at this specific point, the concept that I'm after is this reciprocal of lambda, which is going to be described as a wave number. So therefore in this case, if I try to make this particular reciprocal as a subject, and then from that specific formula I'm going to have the reciprocal of this specific wavelength given as z squared E4m all over 8 epsilon, and then this is going to of course change the value of h, but for our case there where we're having of course the value of h and c for this lower part, which is the denominator part of this specific section of the equation. Therefore it's going to be represented as a square of this h3c, and the rest of course which is part of this Z2 aspect of n1 and n2 is going to remain just as it was. So therefore we're going to have this a particular aspect that we have said, whereby we have said that 1 over lambda is represented, is referred to as wave number, and this wave number can be given or symbolized using this v with a bar at that specific point. So therefore in that sense we are going to have this one represented as, I'm just going to do a substitution for this, and this one represented as a wave number given as such. So therefore from this wave number we're going to find that there's a term that is going to be given a particular notation, basically which is going to be referred to as Rydberg's constant. Now this portion of the equation from a wave number that we have described from the relationship of a photon in electromagnetic radiation is going to be referred to as the Rayberg's constant. Now, therefore, this is going to be denoted, so therefore I've said this part of the equation is going to be described as the Rayberg's constant, and this part of the equation for hydrogen-like species is going to be given as RH. So therefore we can be able to simplify our equation above and give it as the wave number is represented as RH for hydrogen-like species, and therefore we're going to have n1 squared minus 1 over n2 squared. So therefore, this is a simplified way in which we can be able to describe this particular wave number. And therefore, we're going to see that this particular wave number plays a vital role in trying to determine the description of electronic spectra of a hydrogen-like species. Now that we have said this consists of a range of course, what we refer to as constants. This Rayberg's constant can be able to be achieved. If we try to look at this in the first part of this particular formula, this is the number of protons, so this is the charge of an electron, and this is the mass of an electron, permittivity, Planck's constant, and the speed of light. This can be given a value through substitution, which is going to be given as 97. So if you do a substitution for those various constants which are appearing in that particular case, then therefore this is going to be 1.097 times the power of 7 per meter. Now for this case, for other species, of course we have mentioned about hydrogen like species. For other species, we're going to see that this particular equation is going to change, and in this case it's going to consider this particular number that we have mentioned in this particular case, bearing in mind that they'll be having a different atomic number. So in this case, if we were to give a general formula for other species, then therefore I'm going to just do away with this particular constant. So therefore, if we were to give a wave number for other species, then therefore we can just write it as RH, the square over this particular number z, and then we are going to have that difference being given as such. So therefore, these are the two equations that we're going to use in representing the wave numbers of atomic numbers of other species. And this, in an essence, is going to give us a way of trying to describe this specific transition in energy and characteristic of a hydrogen-like species. Now, there are different spectral transitions that we're going to encounter, especially in this hydrogen-like species that we had mentioned in one of our videos. Now, I'm going to have just an illustration so that we can just have a summary of these different spectral lines of hydrogen, so that we can appreciate figuratively how this one can be able to be represented. So I'm just going to do away with this and have that illustration given on the board. Now the illustration is going to give us a clue on the spectral transitions, various spectral transitions that we're going to see for hydrogen species. And therefore we are going to see that for this case we have different names for these various transitions that we're going to see. Of course, we are going to consider this whereby we are going to have the value for n1 at this specific point, showing the transitions from n2, n3, n4, n5, n6, and n7. And this particular transition is going to occur in the UV region of the electromagnetic spectrum, and therefore it's going to of course spectrum, and therefore this is going to give a spectral series that is referred to as a Lyman series. And for the next one, this is going to occur between the N2 and the other levels of the transitions, and this is going to be observed in the visible region. Visible region, of course, that we said appears between 400 nanometers to 700 nanometers of wavelength, and this is going to, of course, be referred to as the Balmer series. Balmer series. And then next there's a transition that is going to occur from the first, which is N3, and therefore this transition is going to be falling from N3, N4, N5, N6 to N3, and this series is going to be referred to as the bus chain series, and this is going to appear, of course, in the region that is the infrared region of that particular spectrum. And then fourth one, we are going to have a transition that is going to, of course, occur from other levels to N4. And this particular transition is going to be making this a series that is going to be referred to as the bracket series. And this also is going to be found in the IR region of the spectrum. And lastly, we're going to have a transition that is going to occur from other higher level transitions to number 5, n equivalent to number 5. And this is going to be referred to as the BFAN series, given as such. This also is going to occur in the infrared region of the spectrum. So therefore, in trying to describe these different types of transitions, therefore we're going to see that the equation that we have developed for explaining the spectral, electronic spectral of this particular hydrogen-like atom is going to assist us in trying to quantify a wave number for various transitions that we have listed on the board. Now, having said that, then we can be able to say that these particular discussions, particularly for describing the electronics spectroscopy of an atom, insofar as it's the extent of the radius from the nucleus, and then describing the transition of the energies, is going to assist us in trying to know various aspects of other atoms that we're going to see later. And now particularly the hydrogen-like species which we have discussed are going to lay a foundation for us in trying to describe other spectral series that we're going to encounter. So for that case, I'd like to welcome us to other discussions which are going to be related to this, and particularly in various topics that we have looked into in quantum mechanics. Of course, if we try to check them from our various description boxes, then we can be able to understand basically the relationship between different concepts that we have discussed so far as this subject of quantum mechanics is concerned. So that is it for now, guys. Thank you for subscribing to our channel, and also thank you for engaging us in the comment section. So I'd like to wind it up there for now, and I'd like to also thank each and every one of us for also contributing. And that is it for now, guys. So bye. God bless you.